Okay, we already in chapter 4 already. So again, chapter 4, we look at three items. One is again on stiffness matrix again, but this time we look at beam. Previously we look at bar. Bar and beam a little bit different. We'll look at beam, and then we will solve problems in a global scale. Means we will look at the assembly of many beam together. And then we'll look at two types of loading. One is concentrated loading, one is distributed loading. Yeah? So again, what is beam? Beam is a long structure. Then if we input some load on both ends, this beam is going to behave like what you see on the screen here. You will do buckling and then bending and even twisting. After we apply the force at both ends. Okay, and there are some notation that we need to take in. The first one is displacement, local transverse displacement. For beam, for beam we focus on y direction displacement, and we do not focus on x-axis direction. If we are in a bar, if you are looking at bar problems, then there is a u and v displacement. We're talking about displacement. Yeah. So previously we learned about F equal to KD matrix. So in bar you will have u and v over here, and okay. But however, this chapter we talk about beam. So beam, we talk about twisting. Twisting means torque or moment or bending moment. Yeah. So what does the moment fundamental equation is that, again, is, let's say this is your surface and this is the interest point, and let's say there is a force. There is a force above this point, and you want to look at, let's say, point A. What is the moment created by this force? This force to the point A. So you look at the distance which is perpendicular to surface and force. The product of F times D, you get moment. Yeah, you get moment at point A. Point cross D. Yeah, or force times D, you'll get moment. So if you look at point 1, all right, why we do not focus on x displacement? It is because if you pull your force to this line, if you pull your force to this line, let me change my pen color. So if I move my force to this point, the D will become 0. So if you take the force times D, you'll get 0 moment at point A. So same with this case. So just take note that for chapter 4, if you talk about beam, we don't have horizontal or x direction moment or torque. So again, for beam, we only look at displacement in y direction. So we have VI. And then for beam, we will look at rotation because there's a twisting moment. There's a twisting angle at a certain point. So we look at rotation. So these two is the displacement for beam. Yeah, is a displacement for beam. Again, F equal to KD matrix. The displacement in this chapter will be displacement rotation, and the notation, how we write the displacement for beam will be V and phi, or pi, if you want to name this one. Yeah? So just remember on that. And then for this chapter, for the left-hand side force, we will look at force and moment. So force and moment. Okay, so be clear of what we covered in chapter 2, chapter 3. We talk even chapter 1, spring, bar. Then be clear what happened when you come to chapter 4. We talk about beam. Yeah. So your coming test will cover chapter 1, 2, and 3. Just pay a little bit more attention. Yeah? Don't mix chapter 4 into your coming test. Yeah? So this is will cover in your final exam. All right. So we have covered up to this all this notation, and then we cover a little bit on equation. So so we cover based on this free body diagram over here, and we arrive at these two equations. So the first, we take all the force in y direction equal to 0. We arrive at the distributed weight here, or load here. So if you have a bar or beam, and you have a loading above the structure, if you see this kind of symbol, it means distributed load, right? So this behavior, it can be sinusoidal loading. Then you can have a weight distributed load also. So on the left here is well distributed. This one we call it distributed load. Yeah. So well distributed means is you have equal loading, and you can convert this one into focus load later on. This one you need to refer to table to convert to focus load. But however, this one we will use formula to calculate the loading at each point, because each point will have a different loading. Yeah. So the first equation last week that you need to remember, start from today, is your distributed load W, which is this one, distributed W equal to negative dV. Again, V here is the displacement in Y direction. Yeah. So Y direction. So why we have a negative sign here after we do this all the force in Y equal to 0? Why we have a negative here? I'm going to explain. You have to understand why there is a negative sign there. So because if you look at beam, if you have a distributed load like that, so again you pull your axis out, X and Y. So the direction of your W and your displacement V. V, normally we have a displacement. We assume all the displacement to Y direction is positive. So you see the displacement and the distributed load or distributed load over here, the direction is different. Yeah, so that's why you get negative there. Okay, yeah, understand? Yeah, Katana. Katana, are you there?
Yes, sir.
Okay, you understand why there is a negative, right?
The direction is it?
Yeah, direction of which one? Of what and what?
Of the force.
Force and what?
And how do we call this?
What is V? What is V?
The y component.
Yeah, Y component. What is that?
The y component of the displacement.
Yes. So it's a displacement in Y direction. Yeah. So
yes.
Yeah. So these two are opposite direction. Very good. Yeah. Okay. So we continue, and we talk. And if we take the second equation, which is all the moment equal to 0 at point number 2 here, so we will get the second equation, which is your displacement V equal to negative dm. dm is your moment, is opposite, yeah. So in this case, again, recall how we define all the notation, all the positive and negative. Okay, I think we have a slide. No, for positive and negative. This one, yeah. So we have all the force. If you have displacement going y direction, V, you will get positive. If you have force also same, going up is positive. And if you have moment anti-clockwise is positive. Yeah? And your rotation anti-clockwise also positive. Yeah. So remember all these principle. Your displacement and force in y direction going up is positive, and for moment and rotation anti-clockwise is positive. Yeah. So these two equations that I showed you just now is important because later on we're going to use this one to build our matrix. Okay, we continue with today's new slides. Okay, now we're going to build the stiffness matrix. Yeah? So if you have a beam that you have a distributed load above the structure. So this one, you have a distributed load in this behavior, and your displacement V here. V is not velocity, yeah? It's a displacement in y direction. So is positive going up. And we look at a tangent point or a radius of our, not radius, a tangent point of a curve at that particular point here. It means we look at a curvature of our curve here. We can define with the rotation angle over here, yeah, phi, or pi here. Right? So, okay. So rho here is your r or your radius. Yeah? So the first equation for today, we learn about curvature. The curvature of the beam K given by 1 over rho, which is, or you can remember as 1 over r. But in this chapter, we will use rho as our curvature of our radius of our deflected curve here. This is equal to is radius, yeah? Radius. So 1 over rho here is 1 over radius of your curvature curve here. We can write equal to moment divided by modulus Young or your elasticity constant value E times the second moment of your area I. So this is the first equation for today. K curvature equal to 1 over r or 1 over rho radius equal to moment divided by EI. Okay. This is the first equation, yeah, for today. And since our beam, we assume our beam, if your beam is having a rectangular cross section, meaning if you cut this beam, then and we look at this direction on the beam, we'll see a rectangular cross section. So if you want to find the I value for rectangular, you have to use BH cubed divided by 12. So this one you learn in your static already. So this one covered in your static module. So you have to remember how to find your I. So if you have a sphere, cylindrical cross section, then different formula. If you have not this one. If you have a I beam, C beam, then your I will be different. Yeah. So a basic one. This is just to show you that what is the I value in this case. So if we have a rectangular, then we have BH cubed divided by 12. However, I think I included there's a new appendix in a Moodle, so I upload already. So you can go and have a look. It's Appendix D, Appendix D in a Moodle that you can refer to. All right. So I think all this you already learned before in your previous module. So again, what is B and H is just the width and the height of the cross section. What important is today the equation over here, curvature K equal to 1 over radius, rho equal to M divided by EI. So this equation is very important. Okay. Now the next equation, or a small definition for slope phi equal to your displacement over x direction. Your slope, this one, the slope of this curvature here, or the gradient of this line. How you find this line is the vertical displacement and the curvature of your object, yeah, of your tube or your beam here with the R. So the definition for the slope here or gradient is given by the differential of your vertical displacement, okay, dv over dx. So we can define our k here. Again, k is curvature. K can be defined by double differentiation of your vertical displacement here, d square divided by x square. It means double differentiation. You differentiate your this term double, and we know that k equal to m divided by modulus Young or elasticity and your second moment of area, EI. So you put these two together, first equation and second equation, you combine, you get the third equation. All right. Then you recall what do you learn in previous class. Vertical displacement equal to negative moment differentiation. Your distributed load equal to negative vertical displacement, differentiation of your vertical displacement. You put these two together. We want to put this term in the term of W. Again, vertical displacement V. Okay, vertical displacement V is linked with moment. Yeah, linked with moment. Yeah. Your loading, distributed load, is always linked with vertical displacement. So this coupling relationship is important. Yeah? So don't link your vertical with the loading here. Don't mix with other. Don't link with the phi. Yeah. So because later you look at another term which is your rotation. Yeah? So okay, let's continue with the slides. So you can write your moment equal to EI, double differentiation of your vertical displacement, d square v divided by x square. You move your EI to the right. Then you substitute your v and w inside there. Okay. Okay, you put in there. Then you continue. So this one you have a look at on mathematics model. So we know that we have a constant EI and we only consider nodal force and moment. We will arrive at EI d power 4 means we differentiate the vertical displacement by 4 times. Power 4 over x power 4, it means you differentiate over 4 times. Okay. So how do we develop the stiffness matrix equation? We have a few steps. So the first one will be we select element type. So what mean by element type? It means that you look at the scenario, and then you look at how many nodes you have. For this example, you have 2 nodes. So node 1 and node 2. In this case is simple case, node 1 and node 2. You can break the structure to 2 node 1, 2, 2, 3. You can break the node into 4 if you want. 1, 2, 2, 3, 3, 4, 4, 5. All these nodes will represent the same structure, the same beam, only the way you solve it. Or in ANSYS, we call it meshing, discretization, mesh. So the smaller you go, the more accurate that you can get the stress inside the structure, right? So for simplicity, in this case, in this diagram, we will break only into 2 nodes here. Okay. Okay. The first steps to develop the stiffness matrix is to know what kind of beam you have. Yeah, you have a single beam or double beam or third beam, and also just not talk about mesh. Sometimes you have 2 beam, sometimes like that. Okay, this is 2 beam, beam 1, beam number 2. So you can label node 1, 2, and 3. Okay, so again, the first step is to look at what scenario you have, and then you label the node number and element number. The first steps, right? Every time you solve a beam question, and if the question asks you to find stiffness matrix, it is important. The first step is you look at the beam, label element. Second step, label the node. Okay, label element, label the node. First step, yeah? Because later you need to write the formula notation later on. Okay, so these are the first steps. Second steps, we define the displacement function. Okay, again, repeat. First steps, define your type, write the element number, write the node. Second, you need to look for the correct equation that replace the behavior of the beam. The function names here is equation. Right, equation. So you have to look for the correct equation that match the scenario that you have. So let's say we have a transverse. We always for beam analysis, we assume that we always have a transverse displacement throughout the length. Okay. This is the fundamental equation when we have a transverse displacement, in this case in y direction. So again, y direction, we use v. V bracket x, it means your v in the function of x in x direction. You have a polynomial equation over here. So a1x power 3 plus a2x power 2 plus a3x and constant value. So this is a polynomial equation. Or when you study about beam, I'm not sure if you already learned about vibration. So this transverse displacement is this equation, this polynomial equation that you see on the screen here, is the beam behavior. Beam behavior for displacement. So if you plot x cubed plus x squared plus x plus a constant value on the Cartesian plane, you're going to see the waveform. So like what you see over here. So step number 2 is look at the proper equation that match the scenario. For beam, we start with the displacement equation, which is the polynomial equation, x cubed plus x squared plus x plus the constant value. Yeah. So remember that when it comes to displacement, step number 2, you need to call out the polynomial equation. What is the basic fundamental form of displacement? Okay, so in here, we see that we have 4 degree of freedom. So 1, 2, 3, 4. Yeah. So this equation just tell you that you have 4 degree of freedom. Okay, this equation just tell you that you have 4 degree of freedom in short. Yeah. Okay. So the next step is that we want to replace this function. We want to express this vertical displacement in the term of V1, V2, rotation 1, rotation number 2. So V sub 1 means vertical displacement at point 1, which is here, V1 at point 1. V2 means the vertical displacement at point number 2. V1 of pi 1 is the rotation at point number 1, transverse rotation at point number 1. V sub 2, it means rotation at point number 2 over here. So we want to put this equation, this displacement function, in terms of these 4. These 4 in the displacement and rotation. How we do it? We apply a strategy called boundary condition. When you solve for static problems or dynamic problems or PC, boundary condition means you input what happened at a certain location x. Normally we will have x equal to 0 and x equal to L, which is the length point, location here and location here. Yeah. So after you have the general equation that you see on the screen here, which is a polynomial equation, and then how you express them in a more proper way, you apply the boundary condition. The first boundary condition is x equal to 0, which is your starting point here. So if you replace x equals 0 in this formula, so v0 equal to x0, this one 0, this one 0, you have only one constant value, which is a sub 4. Currently, we're still at mathematics steps, yeah. And then we also define what is your rotation on a beam is the differentiation of your vertical displacement. So your dv0 divided by x means you take this one. You take your v divided by, not divided, but differentiate on x. So you know that if you have a constant value, this is a constant value. If you have a constant value, you differentiate, you'll get 0, yeah? You'll get constant value, dx, you'll get 0, huh? So this is a constant value, huh? So if you differentiate something constant value, you get 0, yeah? So, and and if you differentiate your v with x here, and you put in 0 there, you'll get your rotation at point 1. We will equal to a3. We equal to a3. Okay. And then if you put in the second boundary condition 1, which is x equal to 0. Boundary condition number 2, where x equal to L. So you put in L inside here. You have AL cubed plus A2L squared plus A3L plus A4. Then you do the same process. You differentiate this equation with x, yeah. So this, then you can rewrite, right? You can rewrite. So I mean that you differentiate this general equation with x. You take dv over dx. You do your mathematics. So the first one, you'll get, Katana, you there? Katana, are you there?
Yes, sir.
Yeah. So if you differentiate the first term here, what do you get?
Yes, sir.
What do you get? If you differentiate this term that I highlight on the screen here over x, what do you get?
Which term? dv dx?
I highlight this one. You differentiate.
Oh, differentiate.
You differentiate
Oh,
a1
with respect to x.
Yes. What do you get?
Get 2a1 x. Sorry, 3a1 x power 2.
Correct. So that's why. Then after that you continue lah. You continue the second one. Differentiate this one. You get 2a2x. Correct. Correct, Katana?
Yes.
Yeah, then this one, if you differentiate with x, you get a3.
Yes.
So you replace with, you substitute your L, the boundary condition L, you get this equation. Right, then we're going to put all these equations together. We're going to find what is your A1, A2, A3, A4 in the term of V1, pi 1, V2, and pi 2 of yeah. So, and then you substitute into this equation. It is a lengthy process, but at least you understand how you get the equation. You apply boundary condition. X equal to 0, x equal to L. Then you differentiate it. Then after that, you go and find what is A1, what is A2, what is A3, what is A4. Okay, then after that you substitute back all these term here, A1, A2, A3, A4, you're going to get this equation, right? It's a very lengthy mathematics equation, mathematics steps, but this is how we do. This is how we get. So at the end, our displacement function in the term of A1, A2, A3, A4, at the end we get in this term. So the first one, we get the first term, x power 3. So you will get your A1 equal to this lengthy equation over here. Then if you rearrange the equation, you'll get your A2 will equal to this lengthy equation minus 3 over L square and blah, blah, blah. That's what you see on the screen here. And then your A3 will be equal to pi 1 or rotation at point number 1. And then your A4 will equal to V1. Okay, so by looking at the screen here, at least you have an idea how you get the displacement function from polynomial equation A1, A2, A3, A4 until you get the complex equation or length, a very long equation that you get at the right hand side of the screen here. Yeah. I don't expect you to memorize all these equations, but at least you understand how you arrive at all this equation. Okay. So any questions so far? Anything that you want to ask me? Anything that you're not clear? No, yeah. Okay. So we continue. After we get the A1, A2, A3, A4 in this in the term of length and your vertical displacement and the rotation terms, then we want to put into matrix form. Want to put in matrix form already. So in matrix form, we express in this general form, which is V equal to ND, which is your displacement, will be on the left, equal to N, which is your shape function, times the displacement. So I think this one is another equation for this chapter. Previously, we have F equal to KD, but this one is another matrix form that link what we learned today. Your V polynomial equation when you write in terms of V and your vertical displacement V and your rotation pi here or phi here. So we want to write in the matrix form V equal to N times D. Your displacement, in this case, you have two type of displacement. One is vertical displacement or transverse displacement at point 1 and 2, plus the rotation at point 1 and 2. And again, what is N? We call it shape function. Shape function is important when you study vibration. In this case, when you study beam, shape function is also important. All right. So again, just memorize this form, this equation, and then we're going to transform this equation in this form. Yeah. So we're going to transform this equation that you see on the screen here in matrix form. Yeah. So we have something called shape function N and displacement that we already defined. Displacement for beam, we have vertical displacement and rotation. So N, we have 4 displacement over here, 4 shape function over here, which is N1, 2, and 3. Because why we know that we have N1, N2, N3, and 4? Because we have 4 degrees of freedom here, because if you have, we talk about a mathematics concept here. So if we have a matrix V equal N D matrix, so you know that your matrix have 4. V, phi, V, 1, 2, 2. So you have 4 on the matrix on the left, on the right here. You know that when you write your matrix, it always follow the degree of freedom on the right here. So like what you did in the previous chapter. You always want to locate them based on their location. Right? So this is your V1, V2, like that. So you have 1, 2, 3, 4, 1, 2, 3, 4. Right? So you have 4 times 4 matrix over here. Okay, sorry, not 4 times 4. We have, sorry, apologize. We have only 4 times 1 times 4. 1 times 4. Okay, now V equal to N D. We know that our displacement V, we only have a constant value. For example, what do I mean by constant value? Displacement, we only have one direction, right? So y in y direction. So when you talk about displacement in y direction, V, let's say we only have like 1 meter to y direction. So how you get one constant value over here while you have 4 term in your displacement here? So you have, let's say I put it in the more general term, A, B, C, D. So when you want to get only one constant value, which is 1 times 1 matrix over here, what is the form over here? You should have A, B, C, D over here, where you have 1 times 4 and 4 times 1. So the product of these two matrices will get you 1 times 1 constant value. So that's why we can predict the form of matrix for your shape function over here. So how you get 1 times 1? You take A times A plus B times B plus C times C plus D times D. The products of all these summation, you'll get one constant value. Okay, so in this case, we will know that our shape function consists of n1, n2, n3, and n4. Clear, Katana? Katana, are you there?
Yes, ma'am.
All right. So, Singi, you back, right?
Yes.
So, okay. Singi, you clear? Why our shape function, we know that our shape function have n1, n2, n3, n4?
Yes.
Understand, yeah?
Yes.
Okay. Lai, are you there, Lai?
Yes.
Okay. When you log in just now, what do I mention? You come in late, right? So when you log in, what do I talk about?
About 1 over R equal M over EI.
Okay, so you are, when you log in, you are at here. This one, right? Okay, good. So again, at this stage, before go for a break, so at this moment, you should know what is the shape function and why your shape function you have n1, n2, n3, and 4. So you match, your if you what you call when you, okay, let me write here again. You know that you have N1, N2, N3, N4. And you know that your displacement D here, you have V1, rotation 1, V2, rotation number 2. If you look at this equation, you have to rewrite all this equation. Means that you have to break all this equation. Xp minus 2L minus 2L cubed V2 X3 and so on. You have to expand all this equation and then you put them together in V1 terms, rotation 1, V2, and rotation 2 terms. All right, then only you can see what is your N1. So your N1 equal 1 over L3, 2 power 3 negative 3x squared L plus L3. So what you're seeing here is mathematical steps. Yeah, it's nothing complex here. Yeah, it's just mathematical steps. What you need to remember is this form, and then you try to make full use of this equation to rewrite it in a matrix form. Okay, yeah. So you expand this equation and then you relocate them according to what is V1, rotation 1, V2, rotation 2. Okay, you put them together. Means you group all the V1 together, you get N1. So for example, how you get this one? How you get this one? So the first one you will get 2x power 3 here if you expand the first one. If you expand number 2 here, you will get 3L square V1 x2. So you have negative 3x here, negative 3x square here. Why we add a L over here? Because for the second term here, if you expand this one, your L is power 2. But if you factor them out, L3, you have to add another L at the back of the term here. Then the third one is your what else? Your V1. V1 is here. The third one is V1, this one. So this V1 is 1 times V1. So when you factor 1 over L3 out there, you have to add L3 in front so that when you cancel out, you still get 1. Understand how you get N1 over here? Singy, you understand?
Yes.
Okay, good. All right. So with this, I think you can do the rest for N2, N3, and N4. Yeah. So I will leave this one as your homework. You go and find what is your N2, N3, and N4. Yeah. But later I'll still give you the answer. Okay. Just want to make yourself clear what is the reason behind how you get all this. Yeah. Okay, for the first session we stop at these slides. We go for 10 minutes break. Yeah. Okay, let me stop the recording.